Our topic here is three-phase AC generation calculations, including wattmeters, which is also part of three-phase AC generation. So first we're looking at the definition of efficiency. So efficiency is equal to the output divided by the input and multiply that answer by 100%. Notice that's not the definition, but the formula. The formula is very simple. The output will always be a smaller number than the input. Please remember that. The definition is the ratio of output power to input power expressed as a percentage. Power factor. What is power factor? Define power factor. Power factor is the ratio of real power to apparent power. How do we know this? According to the formula. Power factor is an indication of how efficient the power is used. Next, define active power. What is active power? It is the real power, that is the capacity of the circuit for performing work in a given particular time. State 4 disadvantages of three-phase generation in comparison with single-phase AC generation. 4 disadvantages of three-phase generation compared with single-phase AC generation. Initial costs are high, not available everywhere, not suitable for most residential applications. Appliances cost more. Okay, so appliances are far more expensive than single phase. A three-phase connected alternator generates 250 kVA at a power factor of 0.9 lagging and has a line voltage of 380 volts. Calculate these questions, pause the video, and then see the solutions. Right, here we are looking at the calculations of three-phase AC generation. So notice in this question it says it's a three-phase star-connected alternator. Notice it has kVA, it generates that amount of power at a power factor, PF means power factor, 0.9, and has a line voltage of 380 V. So the first thing we want to establish what is the power. So notice P is true power, and here they gave us kVA, so clearly we do not have the true power. We will have to work it out. So that power will be the apparent power, and the apparent power is 250,000 volts amps. Then they gave us a power factor of 0.9. Don't forget that power factor is cos theta. Theta is the phase angle. Okay, so theta is the phase angle. Cos theta, the answer of cos theta is 0.9, and cos theta is the power factor. The line voltage is 380 V. And then it's a three-phase system, but it's star system. Okay, so now we have to find the phase voltage. So are the voltages different for star? This is the question you have to ask yourself. So phase voltage is equal to VL over root 3. Substitute our 380 and get an answer of 219.39 volts. So 2 marks for the 1 mark for the answer, 1 mark for the substitution. But remember always to write a formula. Sometimes these questions can be 3 marks. Next, we're looking at active power. So active power is also the true power. In other words, we are calculating P. So the formula P is equal to S cos theta, S being the apparent power. So we'll substitute 250,000 for S and 0.9 for cos theta. Our answer there will be 225,000 watts, and don't forget to simplify it, 225 kilowatts, divide by 1,000. Now reactive power is a little more trickier. right? But the formula, don't forget, reactive power is Q. So Q is equal to S times sine theta. Now notice this is sine theta. This would mean you would need to calculate the angle theta before continuing. So 250,000 times sine, we don't have theta. Right, let's work out theta on the side. So we know that we were given cos theta is equal to 0,9. So bringing cos over, we get 25,84. Substitute it and plugged it into our calculator, and we'll get the reactive power in VAR, volt amps reactive. Simplify that into kilovolt amps reactive. Divide by 1,000. The next question, three-phase delta connected. So this one we know it's delta. The power we do not know because they gave us kilovolt amps. So we know that that is apparent power. So the apparent power is 300,000 volt amps. Why did I write 380? Anyway, 300,000 volt amps. And V phase is 380 volts. The power factor is 0,9. So let's calculate the line voltage. So the line voltage, don't forget, is going to be the same because this is a delta connected system. So V phase is equal to VL, must write it like that, equals 380. So you're showing that it's the same, there's no need for calculation. But because it's 2 marks, you have to put the reason. The reason is that it's delta. The next question, the line currents. So to find the line currents, we can use the power formula. But now, because they gave us the apparent power, we can just use it. If you want to use the true power, you can, but you must use cos theta also in the formula. So now making IL subject to the formula. Okay. So only thing left out here is cos theta because we did not use the true power formula. You can try that, you'll get the same answer. Substituting into the equation, don't forget it's 3000 kilovolt amps, not 380, divided by root 3 times 380, right? All you're going to do is divide that up. Remember to use your calculator correctly, so it's 300,000 divided by root 3 divided by 380. So a quick way to do it is 300,000 divided by root 3 equals divided by 380 again, and that will give you the answer. Right, and it will give us 455,80 amps. Round of two decimal places. If you wrote .8 here, it will be fine. Right, so true power. We know that true power is P. So the formula there is P is equal to root 3 VL IL cos theta. Do remember it's not grade 11, so all the formulas will have root 3 because it is 3-phase. So substituting your values, we know that the voltage here, the line voltage and the phase is exactly the same, 380 because it's delta. Multiplied it by the current that we just worked out, and then times it by the power factor, we get an answer of 269,998 watts. I wrote kilowatts immediately because of space, but that's your first step, to write it as watts. Divided by 1000 will then give us kilowatts, and that will give us 270 kilowatts rounded off. There is an alternative method to work this out. Power equals S cos theta, that is true power, equals apparent power times cos theta. Substitute the apparent power, which is 300,000 times 0,9, which is a power factor, and you will get the exact same answer of 270,000 watts or 270 kilowatts. Okay, and it doesn't get anything more difficult than that in the exam. Right, now we're looking at the watt meters, which is also part of 3-phase AC generation, but it's the second part of the topic. And here it's about connecting wattmeters to measure the 3 watts, the wattages or the powers in those phases. So the first question here says 3 wattmeters are connected to a balanced 3-phase load. Answer the following questions. State 2 advantages of using the 3 wattmeter method. Right? So total power can be measured in a star or delta connected system. Right? So here guys, the question should be state 2 advantages of using a 3 wattmeter method. I made a typo there, I wrote the word 3. Please note this question 311 is state the 2 advantages of using the 2 wattmeter method. So total power can be measured in a star or delta connected system. Only 2 wattmeters are needed instead of 3. Power can be measured in balanced and unbalanced loads. So those are 3 that you can remember. Okay. 312, calculate the total power if the reading on wattmeter 1 is 250. So this one might be tricky to you. So you need to go back to the question. Notice it said 3 wattmeters are connected to a balanced 3-phase load. So if the load is balanced, as we done in experiments on this topic, notice that those 3 wattages will be exactly the same. So your key word there is balanced 3-phase load. Using our formula, power total is equal to wattmeter 1 plus wattmeter 2 plus wattmeter 3, or that formula that's written there. Substituting 450 3 times, okay, and getting an answer 1350. Alright, so notice here the marks will be for the substitution and the answer. State 1 disadvantage of using a 3 wattmeter method. Okay, notice it says 1 disadvantage. Notice it's 3 wattmeter here, not 2 wattmeter. 3 wattmeter, not 2. Please note in 311 that was supposed to be 2 wattmeter method. Right, name 3 wattmeters. Okay, so this system needs 3 wattmeters. Okay, 3 wattmeters instead of just using 2 wattmeters as used in the 2 wattmeter method. So that's the only disadvantage, is that we need 3 meters instead of the 2 meters. Okay. State 1 disadvantage of using the 2 wattmeter method. Notice here it's a disadvantage and it's also 2 wattmeter method. Inaccurate power factor measurement in unbalanced loads. So you'll see now the way it's connected, it'll be hard to measure if the loads are unbalanced. It'll be hard to determine what would be the power factor in each of those loads, because you're only using 2 meters and not 3 meters. Whereas if you're using 3 meters, you'll be able to determine the power factor in each phase. Remember, there's 3 phases. So with 2 meters, it would be hard to determine where is the power factor in each load, right? So let's go here. 3.3 state, 2 wattmeters are connected to a balanced 3-phase system. So 2 wattmeters are connected to a 3-phase balanced system. Wattmeter 1 gives a reading of this, and wattmeter 2 gives a reading of that. So how are we going to find the total power? Very simple. Since it's only 2 wattmeters and you're measuring 3 lines, you're just going to add those 2 values up. So draw the connections of 2 wattmeters. That's our first question. So drawing them, that's our red phase. Then we have our red, yellow, blue phase, and we're going to connect our 2 wattmeters up there. Remember that a wattmeter has 2 coils. One is connected in series and the other one is connected in parallel. Okay, so connecting our series coil, it would be like that. Okay, and then our other coil which would be our potential coil, right? So our current coils are connected in series. To measure current, it's always a series connection. But to measure potential difference, it's always a parallel connection. So this means I'm going to have to connect at those 2 points. And so my voltmeter part of the wattmeter will connect in parallel like that. And the second one also like that. These are your so these are your potential coils. Potential coils. Now, looking at this diagram, notice that the third phase that you connect to, like the previous one, is not in the center, but now it's at the lower part. Pause the video and see if you can draw in the connections. Right, so first I'll close that because that's the series connection of the current coil. Then I will close that because that's the series connection of the current coil. And then I'll connect the voltage measurement, the potential, in parallel. Right? Notice that is the plus of the meter. That is the plus of the meter. The other side should go to negative. Okay. Potential coil. So my potential coil, I must connect that now to the other side, and there is it there. Okay, and this is how we'll connect 2 wattmeters to measure 3 phases. Okay, simple like that. And those are the negative sides of the wattmeter. Notice that the positive sides were there, the negative sides will now be connected there. Right, do study how to connect 2 wattmeters to 3 phases. Very important. And how to draw the diagram. Right, so the next question said calculate the total power. So remember, go back to the question on top. We had 2 powers there, power 1 and power 2, or wattmeter 1 plus wattmeter 2. You can write W1 and W2 in the formula. Substituting the 2 values that were there, we get 18,500 watts. The next question said calculate the power factor. Now this formula is given normally in the formula sheet, but it's in the textbook. Tan theta equals √3. Subtract the powers on the top and add the powers at the bottom, right? And that's the formula. Don't forget this is a times here in between, multiply. So substituting in always the big numbers first and the small numbers on the right. So big numbers on the left, small numbers on the right. Don't forget negatives on top, positive at the bottom. Plugging it into our calculator, we'll get 0.61. Don't forget that it is tan theta that is equal to all of this. So tan theta equals 0.61. Finding the angle, moving tan to the other side, we'll get theta equals 31.38 degrees. Now, we need to find the power factor. This is not the answer. Notice the question said power factor. This is theta. This is the phase angle. So we have to substitute into the formula. Cos theta is equal to, so cos of 31.38 degrees, we will get an answer there of cos theta equals 0.85. Remember that cos theta is the power factor. So the power factor is equal to 0.85. Right, I hope all this was easy and it's doable. You can do it.